Yes. So for Studio 4, we have a arithmetic logic unit that we are going to design. And of course, we don't have all the functionality of an ALU. We have a limited functionality that we are going to design this for. So if you look at the various components that you are going to need for this, and this is detailed in the block diagram that is uploaded on Piazza. So you should, definitely take a look there. So if I quickly bring that up, this is going to be your primary source. So let's take this as well for. So over here we have the bitwise ANDer, bitwise ORer, bitwise XORer, and then the adder. So the adder is the one that you guys designed in Studio 3. So we are going to make this particular component your Studio 3. Not all of it, because some parts of the adder uh, from Studio 3, like the display drivers and the LED display, are now outside. So inside the adder, what you have is what I show over here. So there are four bit full adders. Again, this is something that you guys did the last time. Bit full adder 0, 1, 2, and 3. Each of them is controlled by a series of 8 slide switches, because this is two 4-bit numbers that we are inputting using the slide switches, just as you did in Studio 3. And then this is going to be, the adder module is going to be a structural VHDL code. So this is what you have to write from scratch. You do have the 1-bit full adder from earlier. So in this case, I'm not asking you to make a new one. Just download it from the website or the Piazza site and add it to your project. Then for the adder, you are going to have to make a new structural VHDL module, which means that you are going to do a component instantiation, component declaration, signal declaration. All those steps will need to be done. So please go and take a quick look at Studio 3 video if you need a refresher for that. With respect to component declaration, we did this so that the top level module, in this case the adder module, knows which components you are going to use. Signal declaration was used for all the signals that were outputs, but they were not the final outputs. In this case, that is going to be for C0, C1, C2, right? That's it. Everything else is a final output. And then port mapping or component instantiation was used to connect A to this, B to this, so to connect signal names that are defined inside the components to something that belongs to the entity of the adder. In this case, that's going to be 8 switches. So something very similar to the previous one. So you're going to have to design this adder block, which is now a new structural model that you are going to build. So bit full adder goes inside these. So there are 4 bit full adders there. So that's step number 1. And I assume that this is not supposed to take you too much time. The output is going to be a 5-bit output. The reason is the most significant carry, in this case C3, could be a 1, right? So if we don't have a overflow that we are monitoring, we are allowing the output to go beyond the 4 bits. So we have a 5-bit output here. In fact, of all the components that you are going to design, this is 4-bit, this is 4-bit output, this is a 4-bit output. The adder is the only arithmetic logic unit, in this case arithmetic unit, which has a 5-bit output. So that's step number 1 for the adder. Then these 3 components, which as I consider that to be step number 2, they are going to be pretty straightforward, because in fact they will be almost duplicates of each other. The only thing that will need to be done is the use of keywords and or an exclusive or. They have the same inputs. The outputs you can call that, exclusive or underscore output, whatever you want to call it, inside this block. And then OR output, and then you can call this ANDer output. So that's a 4-bit ANDer, OR, exclusive OR. What does that mean? That means suppose the switches were giving you something like this. You are doing for ANDer, what are you doing? You're doing 1 and 0, 0, 1, 0, 1, like that, right? So that's a bitwise ANDer, and then you would do a bitwise OR, bitwise exclusive OR, and so on. So they have 4 bits at the output here because it's a bitwise operation, and adder is the 5-bit operation one. Then, because you need to select which output goes to the 7-segment display, we are going to need a function select, which is essentially a multiplexer, many to one. So it's going to allow, based on the control signal, it's going to allow one of these guys to go through. So for example, if control is 0, 0, you are going to need 2 bits because you are selecting 1 out of 4. So 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, and this is arbitrary mapping. I'm just in this example saying 0, 0, ANDer goes through. Right? What does ANDer goes through mean? That means that this will appear here. And then for 0, 1, you can have that to be the OR. 1, 0, you can have that to be the XOR going through. But when you come to adder, because it's a 5-bit output, you are going to need 4 bits to go to the display driver 1, and then 1, the most significant bit, will need to go to display driver 2. These are both same components, but copies of each other when you actually write the top level for this, just as you did for Studio 3. And then later on, you have the LED display, similar to Studio 3, and then you control the 7-segment displays using that. So a lot of these things, and to keep things simple, a lot of these things are given to you. For example, what is given? 1 bit full adder is given. You need to write the adder. Let's see. ANDer, OR, exclusive OR need to be written. Note over here, you can write it in a very, very effective manner. So if you have a vector 3 down to 0 called input 0, you can AND all at once. So if you have to do, so you don't need to do it bit by bit. If you do input 0, which is a vector 3 down to 0, and input 1, which is also a vector 3 down to 0, if you use one keyword, it already does the bitwise AND for you. In other words, you don't need to do it like input 0 with ANDed with input 1 of 0 and so on. You don't need to do it four different times. You can just write it in one statement. And then once you do the ANDer, copy paste your code 2 more times, change the AND to OR and exclusive OR, and you will be done. So I don't think that takes much time as well. But they are going to be new behavioral models. Now coming to the next block here, which is given to you, function select. Function select is the selector, right, between which output goes to the 7-segment display. Now, this is a new type of VHDL code, the procedural VHDL code. So we have looked at behavioral, we have looked at structural in the previous lab, but now we are introducing a concept of procedural VHDL code. And this can be explained in a better manner if I show you this. If I show you an example code. So I'm just going to pull up the function select. No. Hold on, let me monitor the chat. The chat box, let's see. So Anthony says, how will cin work? Let me go back here and take a look at cin. Right. Cin, you can attach that to a switch. So just as you had an initial carry in for Studio 3, you can use a switch to connect to carry in over here. You can assign that to a switch. Then the next question is, I added bit full adder 0 as a design source, but there's no code there. I would recommend that you um, save the VHDL files. So right click on those files on Piazza, save them maybe on desktop or some place on your computer with the extension .vhd, and then when you're ready, after you create a new project, you say add existing source and you select all the VHDL source at once if you want it, and then you can add all of them together. But uh, for for me, it does show up with the code. Anybody who is listening facing the same problem? Do you guys see?
You can even try to open it in Notepad just to make sure that the file you downloaded actually downloaded properly, because you should see the code there if you just open it in Notepad to take a look at it. If
Right.
you don't see that there, you may need to re-download.
Okay, let me do it, and let's see if I can also show you guys. All right, let me do share content here, and all right, I know. All right, I hope you guys are still able to hear me. And
Yes.
now what we can do is I can show you this. Go down, and then if I click on this, say if I click on this, what happens? It downloads it, right? And it downloaded as .vhd, and it downloaded in my downloads folder, which is fine. But if I do show all here, come on, let's go show in folder, and then I'm just going to open it like Lawrence suggested. I'm just opening that file up in Notepad, and it opens with that code, which is exactly what I want. So, if you are having difficulty with adding the sources, you could also do this, right? You could create a blank source and then copy paste the code from Notepad to your Vivado project. So you can do that as well. Now, coming to the one that I wanted to talk about, let's see here. Function select. So I'm going to right click and I'm going to say, sure, I just click it. Okay, I downloads it. And then I'm going to open it up in Notepad and talk about it for just a few minutes. So, like I said, this is a procedural VHDL code, slightly different from the two that you have seen before. This also falls in the category. This particular one falls in the category of behavioral. So it's sort of a procedural VHDL module, but it has a behavioral aspect to it, which means that I'm explicitly mentioning the relationship between outputs and inputs. So architecture, why are we calling it procedural? Because you see, we use this process keyword and we say it is a process which depends on input 0, input 1, input 2, and control, which means this piece of code will execute every time one of these four inputs changes. So if there is any change in control, input 2, input 1, input 0, due to maybe you pushing a button or flipping a switch, every time there is a change in one of these, this code will execute. So it will not execute all the time, it will execute only when one of these changes. So that's the procedural code, which is indicated by the keyword process. Here there is a very simple case statement, in this case 4 case statements being used, similar to the case statements that you used in the Studio 2. That was the 7 segment display decode, the 7 segment on the 7 segment display. Over here, when control is 0 0, you're saying output is 0 and input 0. That 0 is for the most significant bit. Remember, it has to be 5 bits. So the most significant bit is 0, and then whatever comes out of the ANDer, whatever comes out of the ORer, whatever comes out of the XORer, and then input 3 is, in this case, the output of the adder, right? So that's your function select block. You can use it, but I also wanted to talk about, while you are using it, what is this doing, right? So it is functioning like a selector when one of these things change, and the function select block doesn't execute unless the output of the ANDer changes, output of the changes, output input 2 changes, or control changes. All right, so let me minimize that and then go back over here. Let's see, share screen. All right. So there's the next question. Are we implementing AND using exclusive OR in XOR? No. So we are ANDer is bitwise AND. ORer is bitwise OR. Exclusive ORer is exclusive XORer, right? So, it is the same inputs. These blocks will evaluate the outputs here, but only one of those outputs will go forward depending on what control you give. And you can use, two push buttons to control which output goes through. For the control, it's a two pin signal. So each of these blocks does the AND here, 4-bit AND, 4-bit OR, 4-bit XOR, and 4-bit add. But those outputs are available all the time, but only one of them goes through depending on the control. And then after that, it is the display driver 1 and 2, similar to what we had before, and then the LED display component. Essentially, what do we need to do to represent this 4-bit output in a hexadecimal format on a 7-segment display, right? So those are, you don't need to write those, and I mentioned that over here. You don't need to write the 7 display driver or LED display. You just need to add that to your project, just as you did from the previous one. So that's essentially your Studio 4. And to check things, you have a certain test cases that you are going to have to test for. All right. And you have certain columns, right? You have expected output in hex, and then whatever you actually see on the 7-segment display based on the experiment. So I hope you would agree that both of these should match up if you do this right. Okay, that's all I have. What I'll do there is stop the recording, and then I can take your questions.